In the first part of the lecture on recurrence formula, actually we have derived two recurrence formula, and you can see actually there are 6 recurrence formula, and in first lecture we have derived this first 2 recurrence formula. Now today we are going to discuss or derive the remaining 4 recurrence formula. So now first of all we will see the derivation of this third recurrence formula, which is 2n plus 1 into Pn of x equal to Pn plus 1 prime of x minus Pn minus 1 prime of x. So now let us see the derivation of this third recurrence formula. I have again mentioned here this third recurrence formula, and actually we will start with the first recurrence formula, which we have already studied earlier. And starting with first recurrence formula, we can get the result, which is third recurrence formula. You can see I have mentioned here that the first recurrence formula, which we have studied already, is 2n plus 1 into x Pn of x equal to n plus 1 Pn plus 1 of x plus n Pn minus 1 Pn minus 1 of x. Now let us differentiate this equation or this relation with respect to x. So you can say differentiating with respect to x. We have, when you will differentiate it with respect to x, what will be the result? You can see in LHS 2n plus 1 is a constant factor, so it will be outside of the differential operator, and we have to differentiate the product of these two functions, that is x and Pn of x. So actually we will use here the rule of differentiation of product of two functions. So here x is first function, so if you take this x at age, then there will be derivative of Pn of x, and what will be that? That will be simply Pn prime of x, and plus now we will differentiate this x, and derivative of x with respect to x will be simply 1, so this will be only Pn of x. And in RHS you can see this n plus 1 is again a constant factor, so it remains at age, and derivative of this Pn plus 1 of x will be simply Pn plus 1 prime of x, and plus in this second term you can see n is a constant factor, so this will be n Pn minus 1 prime of x. So after differentiating this equation with respect to x, we get this result. Now you can write this expression like this. This is 2n plus 1 into x into Pn prime of x plus 2n plus 1 into Pn of x. Actually I have multiplied by this factor 2n plus 1 to the both terms, and this is simply equal to n plus 1 into Pn plus 1 prime of x and plus n Pn minus 1 prime of x. Let us say this is equation 1. Now you have already studied the second recurrence formula. You can see here we have already studied it. This is n Pn of x equal to x Pn prime of x minus Pn minus 1 prime of x. So write this second formula here. You can see this second formula is this much, and from this second formula we can write from second recurrence formula. second recurrence formula. You can see what is this second recurrence formula. See here, this is n Pn of x, n Pn of x, and this is equal to x Pn prime of x minus Pn prime n minus 1 of x. So this is x Pn prime of x, x Pn prime of x, and minus what? Minus, you can see this is Pn minus 1 prime of x. This is Pn minus 1 prime of x. And so from here we can easily write that this is x Pn prime of x, and this will be equal to what? This will be n Pn of x plus Pn minus 1 prime of x, and say this is equation 2. Now we will make the use of this equation 2 in this equation first. So you can see in the first term in LHS of equation 1 there is a factor x into Pn prime of x, and in this second equation we have defined by the second recurrence formula this factor x into Pn prime of x. So let us put the value of this x Pn prime of x in the first equation in first term. So using, you can say, using equation 2 in 1, we get what will be our result. You can see actually we will substitute this value of x into Pn prime of x in this first term. So you can see what will be the result. In fact, after substituting that value, our result will be 2n plus 1 into n Pn of x and plus Pn minus 1 prime of x. This is actually the value of x into Pn prime of x, and plus, you can see here the next term is what? The next term is 2n plus 1 into Pn of x. So this will be plus 2n plus 1 into Pn of x, and that is equal to what? You can see here this is equal to n plus 1 into Pn prime Pn plus 1 prime of x plus n Pn minus 1 prime of x. So write this RHS here. This will be n plus 1 into Pn plus 1 prime of x and plus n Pn minus 1 prime of x. You can see. Now actually we will simplify this result. So you can see here, in fact, this 2n plus 1 into n Pn of x and this 2n plus 1 Pn of x. In fact, when you will associate these two terms, this 2n plus 1 into Pn of x will be actually as a common factor. So taking this as a common factor, that is 2n plus 1 and Pn of x, we will take it as a common factor. So this will be n plus 1. In fact, in this first term n will remain, and in this second term only 1 will remain, and Pn of x is as a common factor. So we have associated this first term in LHS and this third term in LHS. And now take this term, that is 2n plus 1 into Pn minus 1 prime of x into RHS. So what will be the result? This is n plus 1 into Pn plus 1 prime of x and plus n into Pn minus 1 prime of x and minus, now take this term 2n plus 1 into Pn minus 1 prime of x into RHS. So this will be actually minus 2n Pn minus 1 prime of x and minus Pn minus 1 prime of x. I have taken this second term in LHS in RHS, and so this becomes negative. So now you can see actually here is minus 2n Pn minus 1 prime of x and here is n Pn minus 1 prime of x. So when you will actually simplify it, what will be the result? You can see this is n plus 1 into Pn plus 1 prime of x and and here is P prime minus P prime n minus 1 of x. So when we will take this Pn minus 1 prime as a common factor, then what will be our result? You can see this will be minus n plus 1, because I have taken this minus as a common factor, into Pn minus 1 prime of x. In fact, this in RHS, these last three terms are associated, and so our result is like this. Now you can see that this RHS, in RHS, n plus 1 is a common factor. So take it as a common factor. So this is n plus 1 into Pn plus 1 prime of x and minus Pn minus 1 prime of x. Now you can see in LHS there is a factor n plus 1, in RHS there is also a factor n plus 1, so that will cancel out, and therefore what will be our result? Our result is simply 2n plus 1 into Pn of x and this equal to Pn plus 1 prime of x minus Pn minus 1 prime of x. And you can see this is actually the result which we have to prove. 2n plus 1 into Pn of x equal to this much. So you can see our third recurrence relation has been proved here. So although it is a proof, but you should remember these results to solve the numerical problems. Now we will see the proof of the fourth recurrence relation. So again I am writing here first of all what is this fourth recurrence formula or relation, and after that we will prove that. So see, I have mentioned here the fourth recurrence formula. You can see here this is Pn prime of x equal to this much. So I am again repeating this result here. So you can see the fourth recurrence formula is Pn prime of x is equal to what? This is x into Pn minus 1 prime of x and plus n Pn minus 1 of x. In fact, we can also write this fourth recurrence formula in this manner, which I have mentioned here. So again I am repeating another form of it. So you can see, we can also say that the fourth recurrence formula is n plus 1 into Pn of x, and this is equal to Pn plus 1 prime of x minus x Pn prime of x. So these are this is actually the fourth recurrence formula, and now we will again see its proof. So to prove this recurrence formula, we will start with the third recurrence formula, which we have just obtained here. You can see we have obtained the third recurrence formula in this equation. So this will be our starting equation, and starting with this third recurrence formula, we can arrive at this result which has been defined in this fourth recurrence formula. So now let us rewrite this equation, which is known as third recurrence formula. So you can say, according to third recurrence formula. So according to recurrence relation 3. According to recurrence relation 3. You have seen just now that this third recurrence relation is what? This is 2n plus 1 into Pn of x, and this is equal to Pn plus 1 prime of x minus Pn minus 1 prime of x, and say this is equation 1. So one thing is remarkable, that if you want to prove the recurrence formula, definitely the previous formula must be in your mind. So apart from this proof, you must remember this formula, and that will be also helpful in solving the problem. Now you have seen again the second recurrence formula. You can see here, actually the second recurrence formula we have mentioned here. You can see this is the second recurrence formula, and from this second recurrence formula we can find the value of this x Pn prime of x. We should write it in at each. So write this second recurrence formula here. So now from recurrence relation 2, and you have just seen what is recurrence relation 2. This is actually n into Pn of x, and this equal to x into Pn prime of x minus Pn minus 1 prime of x. So say this is equation 2. Now simply subtract this equation 2 from this equation 1. So you can see, subtracting equation 2 from equation 1, we get. This is just a simple mathematical step. You can see, in fact, in LHS of the first equation, there is 2n into Pn of x, I am just multiplying, plus Pn of x and minus LHS of equation 2 is what? This is n Pn of x. So this will be minus n Pn of x. And this will be equal to, now see the RHS. In fact, in RHS you can see there is Pn plus 1 prime of x minus Pn minus 1 prime of x. And now we will subtract this much. So this is minus x into Pn prime of x, and here minus minus will now become plus. So this is plus Pn minus 1 prime of x. Now you can see this term and this term will cancel out, and see this LHS. 2n into Pn minus x minus n into Pn of x. So what will be this? This will be actually equal to n into Pn of x. And here is Pn of x. So this is Pn of x. And that is equal to, you can see, this Pn plus 1 prime of x and minus x into Pn prime of x. Now you can take this Pn of x in LHS as a common factor. So this will be n plus 1 into Pn of x, and that equal to what? That will be equal to Pn plus 1 prime of x minus x into Pn prime of x. Now say this is equation 3. Now you can see in our result, actually we have to prove this n Pn prime of x equal to this much. But in our equation is actually n plus 1 Pn of x. So you should remember here one trick. We will simply replace this n by n minus 1. N by n minus 1. So replacing, because you know this is valid for any value of n. So replacing n by n minus 1 in 3, in this equation 3, we get, you can see, when you will replace this n by n minus 1, so that will be n minus 1 plus 1, and here will be n minus 1. So what will be in fact the term in LHS? You can see there will be in fact n minus 1 plus 1 into, there is Pn of x, but now we will write n minus 1 at the place of n. So Pn minus 1 of x. And again in RHS there is the term P prime of n plus 1. So n will be now replaced by n minus 1. So this will be n minus 1 plus 1 of x, and minus x into Pn prime of x, but n will be now replaced by n minus 1 of x. So now you can see this 1 and this 1 will cancel out, and our result will be n into Pn minus 1 of x, n into Pn minus 1 of x, and this equal to, here also this 1 and this 1 will cancel out. So this is simply P prime n of x and minus x into Pn minus 1 prime of x. And so you can write from here that this Pn prime of x, this term, I am writing expression for this term. So take this term in RHS, in LHS, and your result will be what? This will be simply n Pn minus 1 of x and plus x into Pn minus 1 prime of x. And you can see this is actually our recurrence relation defined in the fourth relation. So this is your fourth recurrence formula or recurrence relation. Now, as I have mentioned in this fourth recurrence relation and another form, which is n plus 1 Pn of x equal to P prime n plus 1 of x minus this much. So to get this result, you can see that the multiple of this Pn of x should be equal to, in fact, n plus 1. That should be equal to n plus 1. So now in this result, let us say this is equation 4. If we will replace this n here in this equation 4 by n plus 1. So replacing n by n plus 1 in equation 4. What will be our result? You can see n will be replaced by n plus 1. So in LHS you will write Pn plus 1 prime of x, and that equal to, here is n, so n will be replaced by n plus 1, and here again n will be replaced by n plus 1, and since there is n minus 1, so this will be n plus 1 minus 1 of x, and plus x P prime n minus 1. N will be replaced by n plus 1, and there will be minus 1 of x. And so you can see what is our result. Pn plus 1 prime of x, and this equal to, here this 1 and this 1 will cancel out, so this is n plus 1 into Pn of x, and this, this is plus, so this will be plus, again here this 1 and this 1 will cancel out, so this is x Pn prime of x. So you can see from this result we can write that this term n plus 1 into Pn of x equal to what? This will now take this term in LHS, although I am writing it in RHS. So this will be P prime n plus 1 of x minus x into Pn prime of x. And you can see this is the result which we have to prove. So this is the another form of fourth recurrence formula. Now we will prove the fifth recurrence formula. You can see. So first of all, again I will write the fifth recurrence formula and then we will prove that. So for this you can see what is this fifth recurrence formula. You can see I have mentioned it in the beginning, so you can see it here. So this is your fifth recurrence formula. You can see here 1 minus x square into Pn prime of x equal to this much. So I am again repeating this. the fifth recurrence formula, and after writing this relation, then we will prove it. So you can see the fifth recurrence formula is 1 minus x square into Pn prime of x, and this equal to n times Pn minus 1 of x minus x times Pn of x. This is actually the fifth recurrence relation or recurrence formula. Now, starting with the fourth recurrence formula, which we have just proved, this fourth recurrence formula, you can see here, we can get the proof of the fifth recurrence formula. So let us start with the fourth recurrence formula. So you can say, so from the recurrence relation, number 4, you can see the fourth recurrence relation is what? This is in fact Pn prime of x equal to x into Pn minus 1 prime of x and plus n Pn minus 1 of x. This is actually the fourth recurrence relation. Now you can see I can write this as Pn prime of x minus this x times Pn minus 1 prime of x, and this will be equal to n times of Pn minus 1 of x, and let us say this is your equation 1. Now again we will make the use of the second recurrence formula. So you can say from second recurrence relation, or you can say recurrence formula. So I have told you, you must remember it. So I am just writing it directly. From this second recurrence relation, you can write that x into Pn prime of x minus, I have arranged this some terms here, Pn minus 1 prime of x, and this equal to n into Pn of x, and say this is equation 2. So this is simply the second recurrence relation, and now multiply this second equation. See this second equation and multiply this second equation by x, and after that we will actually subtract that result from this equation 1, and then you will see that your fifth recurrence formula will be simply proved. So let us multiply equation 2 by x. When you will multiply, you can see this will be simply x square into Pn prime of x minus x times Pn minus 1 prime of x, and that equal to n times x into Pn of x, and say this is equation 3. Now we will subtract this equation 3 from this equation 1. So you can see subtracting subtracting equation 3 from equation 1, we get, you can see this, when we will subtract this equation 3 from equation 1, in LHS you can see this Pn prime of x minus this x square Pn prime of x. So in first term, this Pn prime of x will be as a common factor, and the multiple of that will be 1, here will be 1, a minus x square. And this second term in the equation 1 will remain at ease. You can see here, because, no, sorry, this second term will be in fact cancel out, because this second term is minus x Pn minus 1 prime of x, and in this equation 3 also the second term is same and sign is also same. So after subtracting equation 3 from 1, this second term will cancel out. So you can see what will be your result. So, so I have mentioned here that subtracting equation 3 from equation 1. So our result will be 1 minus x square into Pn prime of x. And as you have seen that the second term will cancel out in LHS. So now see the RHS of these two equations. In RHS here is n into Pn minus 1 of x, and in this is equation, in this equation third, the RHS is nx into Pn of x. So you can see only this n will be a common factor, and the remaining factor will be Pn minus 1 and minus x Pn. So you can see here, this will be simply n into Pn minus 1 of x minus x into Pn of x. And you can see actually this is n, this is n, and you can see this is actually the fifth recurrence relation which I have mentioned just now here, and you can compare that this is the fifth recurrence relation. So in this way you can prove the fifth recurrence relation. Now we are going to prove the last, that is the sixth recurrence relation. So again I will first of all mention that the sixth relation, and after that we will prove it. So you can see I have mentioned earlier in the beginning all the 6 recurrence relations. So you can see it here that this is actually 1 minus x square Pn prime of x equal to n plus 1 x Pn of x minus Pn plus 1 of x. So again I am writing it directly, and then we will prove it. So you can see the sixth relation is what? This sixth relation is 1 minus x square into Pn prime of x, and this equals n plus 1 times x into Pn of x minus Pn plus 1 of x. This is actually the sixth recurrence formula. Now we will see its proof. In fact, for its proof, we will again start from the recurrence relation defined in 1. So you can write the recurrence relation 1 may be written as may be written as. You can see you have already seen this relation several times and you should remember it. So after some simplification, this first recurrence relation can be written as n plus 1 into x Pn of x plus nx Pn of x. In fact, you can see in the first recurrence relation there is 2n plus 1 into x Pn of x. Actually, this term has been splitted into two terms, n plus 1 x Pn of x, and again, in fact, n x Pn of x. So after adding those terms, you will get the original term. So I have simply divided this first term in LHS of the first recurrence formula in two parts. So this is n plus 1 x Pn of x plus n x Pn of x. And this is equal to what? This is actually equal to n plus 1 into Pn plus 1 of x and plus, n into Pn minus 1 of x. Pn minus 1 of x. Now, let us simplify this result. You can see in RHS there is a term containing the constant factor n plus 1, and in LHS2 there is a term containing this constant factor n plus 1. So let us bring this term in RHS in LHS and associate with this term. So you can see this n plus 1 will be then a common factor, and here in LHS the term will remain, which is x into Pn of x. And when we will bring this term in LHS, then n plus 1 has been taken as a common factor. The remaining factor will be minus Pn plus 1 of x. So this will be minus Pn plus 1 of x. And now we bring this term in LHS, which is nx Pn of x, in RHS. So in RHS you can see here is n, and this term remains in RHS, and here is also n. So we will take this n as a common factor, and so this will be what? Pn minus 1 of x. And when this term will be in RHS, sign will be just reverse, that is minus. You have taken this n as a common factor, so this will be minus x into Pn of x. Pn of x. Now, see the fifth recurrence formula. You can see here. In fact, you can see the RHS of this fifth recurrence formula. In fact, n into Pn minus 1 of x minus x Pn minus x minus x Pn of x. What is this? Actually, this is equal to 1 minus x square Pn dashed of x. So you can see this term in RHS of this equation, by the use of this formula, that is fifth recurrence formula, can be replaced by simply by 1 minus x square into Pn prime of x. So you can say using the recurrence relation 5, recurrence relation 5, what will be our result? You can see this will be n plus 1 times x times Pn of x minus Pn plus 1 of x, and this equal to, as I have told you, this RHS will be replaced by the result which has been defined in this fifth recurrence formula. You can see this is actually equal to 1 minus x square into Pn prime of x. So we will write here 1 minus x square into Pn prime of x. So you can now rewrite this term in RHS in LHS, because I have written here in LHS. So you can say this 1 minus x square into Pn prime of x, this is equal to what? This is equal to n plus 1 times x into Pn of x minus Pn plus 1 of x. So actually this is the sixth recurrence formula. So we have actually now in these two lectures proved all 6 recurrence formula. In fact, in the forthcoming lectures we will discuss some of the problems, or you can say the solution of problems based on this recurrence formula.